So then, without further ado, let me introduce Bryan Holler, who's a scientist at Space Telescope Science Institute, and his presentation is exploring our solar system minor body population with Roman. Take it away.
All right. So, you can see my PowerPoint, correct?
Yes, we do.
All right. So, thanks for joining early. My name is Bryan Holler. Be talking about a more or less a more unique topic at this conference, our own backyard solar system, particularly the minor body populations, and what Roman can do for our studies of those objects. So, despite not having a requirement to support moving target tracking, Roman is still certainly more than capable of revolutionizing the study of minor body and irregular satellite populations within our own solar system. Since there is no IFC any longer, the moving target tracking requirement is not necessarily all that important. So you can still use the WFI, its large field of view and sensitivity for more efficient imaging to probe the solar system even deeper than before, to look for smaller objects at further distances. I'll point out that a lot of this talk comes from a paper published in 2018, available on arXiv, shown here. And I'll put this up again at the end of the talk. Sorry for my dog. So some of the material in that paper, back when the spacecraft or the telescope was called WFIRST, before it was renamed, includes a discussion of what you can do with the IFC, which obviously is no longer available. But in general, for the WFI, a lot of the content is still valid. So we're all aware of the field of regard of Roman. Solar elongation angles from 54 to 126 degrees. But this has some special significance for solar system studies. Obviously, we can't look at things within the Earth's orbit or too far within the Earth's orbit, including Venus, Mercury, and the Sun, and including the Earth itself and the Moon. And we also can't look at opposition when objects are unfortunately at their brightest. But there's still plenty of objects that can be observed, as I'll try to describe now. So here's a cartoon version of the solar system. I point out at the bottom, this says not to scale. This is Earth, Mars, Jupiter, and Neptune. And point out that we can observe objects in the main asteroid belt between Mars and Jupiter, including main belt comets in this region. The Jupiter Trojans that orbit ahead of and behind Jupiter, 60 degrees ahead of and behind, as well as the Centaur objects, escapees from the Kuiper belt that are transitioning into short period comets, and they have semi-major axes between Jupiter and Neptune. And then beyond Neptune, we have the trans-Neptunian objects, semi-major axes greater than 30 AU, and a wide variety of dynamical populations in this region, including those that are in resonance with Neptune, those that are on orbits that no longer interact with Neptune, the extreme TNOs, and then everything in between, the classical objects. It's also plenty to do with the irregular satellites of the giant planets. These are objects orbiting on high inclination, retrograde orbits, for instance, and thought to have been captured from heliocentric orbit at some point in the past. The question is when. I show the near-Earth asteroids interior to Earth's orbit, but of course we would observe them when they're exterior to the orbit, assuming that the tracking rate for Roman is fast enough to observe some of those targets. Additionally, there are other Trojan populations of Neptune, Earth, and Mars, with the population at Neptune potentially being even larger than the population at Jupiter. We still have not obviously found enough of those objects to confirm that theory, but it's a possibility. And more recently, there's the two unique cases of interstellar objects. We obviously can't study the two that we have previously seen, but there should be a few that should be observable per year. And Roman hopefully will be able to discover a few more of these. And last but not least, the long period comets on similar kind of orbits coming in from the Oort cloud for a once in a million year opportunity past the sun. So I'll focus in on the inner solar system first and try to move outwards. One particularly interesting class that I'd mentioned on the last slide are the Earth Trojans. When I've given a version of this talk before, I've said that there's only one Earth Trojan known. It was discovered over 10 years ago, but we now know of two. As of last year, there are two Earth Trojans now. And this new one is on an even more stable orbit than the previous one, but they're thought to exist in this population for maybe a few thousand years. So it's important to study these objects due to their proximity to the Earth. Not only study their origins, but also the potential for future robotic and manned space missions. It doesn't take a whole lot of delta V to get to something sharing the orbit with the Earth. So the more of these objects that we know of, the more opportunity we have to potentially study objects very, very close to home. Unfortunately, for most space-based assets, you can't look at the right angle to study these objects. And from the Earth, you have to stare into the very bright twilight to see these tiny rocks that you're not even seeing at full illumination. You're seeing at a certain phase. But with Roman, you actually have, with the field of regard, you can view objects at these positions, potentially increase the number by a significant fraction, by orders of magnitude. You don't have to look through twilight, and the thermal requirements allow you to look in that direction. Moving a little further out, the irregular satellites, I show a picture of, I believe, Saturn on the left there, the irregular satellites there. These are populations of bodies that were captured from heliocentric orbit, most likely from primordial populations, but there's a possibility they could be captured from currently existing populations. That's an open question. They orbit, highly inclined orbits, retrograde orbits, large semi-major axes, large eccentricities. So you can imagine that, over time, as they're captured, there could be collisions. You can get collisional processing. I'll talk about that on the next slide. And we have two instances of Phoebe at Saturn and Triton at Neptune that provide our best evidence of a Kuiper belt origin, so beyond Neptune. But that's only two objects. There are hundreds of known irregular satellites, and understanding where they came from is important for dynamical history, understanding the dynamical history of the solar system. So in terms of when they're captured, these obviously wonky orbits can result in some collisions, and these have been studied, and a lot of these objects have been categorized into families, the same way that we have asteroid families in the main asteroid belt. These objects share similar compositional properties, like color, things like that, as well as similar orbital properties. And on the left here, I show a cladistics diagram from Holt et al. 2018, applying a biological concept of cladistics to solar system objects for the first time. So understanding these collisional processes around the giant planets, comparing them to other populations such as the main belt, such as the trans-Neptunian region, where we know of one collisional family at this point in time, help understand the collisional processes going on in the solar system. Do we have the same kind of size frequency distribution for these objects? And what does that say about the processes that form them? And obviously, to fill out the size frequency distribution, you need to go to smaller sizes, which is something that we have yet to do. So let me just move this real quick so I can see it myself. The smallest satellites discovered around each of these objects, we have 1 kilometer for Jupiter, 300 meters for Saturn, 18 kilometers for Uranus, and 35 kilometers for Neptune. With Roman, we can drill down to even smaller sizes for most of these planets, especially Uranus and Neptune. Completely revolutionized our understanding of the irregular satellite populations of the ice giants. But even for Jupiter, we can go down to 300 meters instead of the 1 kilometer that we currently know. For Saturn, we can't quite get down to the currently known smallest size due to Cassini. Cassini did a pretty good job of identifying some new irregular satellites at small sizes, but perhaps fill out some of the region just above in size range for that. And where Roman will really excel is using the WFI to cover the Hill spheres of these planets with incredible efficiency. So the Hill sphere is the stable region surrounding a planet where a satellite can orbit rather than being pulled into heliocentric orbit. And obviously, the larger the planet, the larger that Hill sphere is, and the closer to Earth, the larger it appears in the sky. So Jupiter's Hill sphere is very large. I forget exactly how big it would appear on the sky if it were a solid object, but you'd certainly be able to see that with the naked eye. Roman, the WFI can cover that entire area in only 17 separate pointings. And then for the ice giants, it would only take 6 pointings. So with that kind of efficiency, we can certainly cover a large area as well as come back over time to study the orbits of these objects, which some can last for years around their giant planets. So it's worth coming back to characterize the orbits. Taking a small detour in the solar system, talk about stellar occultations real quick. So when a foreground body passes in front of a background star, you see a dropout of light, a tiny shadow is cast across the Earth. And this can obviously occur anywhere from the main belt asteroid outwards to the trans-Neptunian region. We've used this to identify Pluto's atmosphere back in the late 80s. You have instead of a sharp drop when you hit the edge of the body, there's a more steady decline as the star passed through Pluto's starlight passed through Pluto's atmosphere. And it's also been used to identify the rings around the Centaur Cherrycloe and the TNO Haumea. This is such a powerful technique, actually, that you can that it's even been used to study a canyon on a trans-Neptunian object. Now, the possibility for a track of a known object, the shadow path to cross exactly where Roman is in L2 is pretty small, obviously, but nevertheless, it's something that's being attempted with James Webb. Going to try to capture an occultation with James Webb at the same location. But the more important thing for Roman is the ability for serendipitous occultations. So catching an object at any distance in our solar system passing in front of a background star. Each of the 18 detectors of the WFI is capable of obtaining a guide star during any observation. So in practice, that's not always going to be the case. You don't need all 18, and there might not be even guide star candidates available in all 18 detectors. But the possibility of getting a few during any observation that is occurring doesn't just have to be a solar system observation. Anything as part of the core community surveys, transmitting the guide star data down to Earth, with these small patches, small subarrays being read out at 5.8 hertz, would provide a large data set to search for serendipitous occultations. This has been done with Hubble guide star data before, with potentially 2 separate instances detected. And that was making use of, I believe, 1 or 2 different guiders. So if we had a small handful going on for each observation, you're significantly increasing the chances of making a detection of serendipitous occultation. And the importance there, if you haven't figured out, I'm mostly a trans-Neptunian object researcher, so I've focused a little more on that kind of topic in this talk. But for the serendipitous occultations, we can study the smallest TNOs this way. We're talking tens of meters, right? These are the kind of objects that you can't even detect with spacecraft flying through the trans-Neptunian region unless they're really close. So the only way to study these very small objects at very large distances is to wait for them to pass in front of a background star. We have an idea from craters on Pluto and Charon and Arrokoth, flown by New Horizons. They provide an indirect view of the size of the impactor population in the Kuiper Belt, in the trans-Neptunian region. And we find that shortward of 10 to 15 kilometers in diameter, there's a dearth of objects, at least compared to the asteroid belt. So it says something about the collisional grinding going on in the Kuiper Belt, and that it might not have been as robust as that in the asteroid belt. So we obviously need to be able to more directly observe these smallest objects rather than trying to infer indirectly from the crater populations. And those serendipitous occultations are, at this point in time, the only means of identifying objects on the scale of tens of meters at tens of AU, but it is possible. And possibly my favorite topic with Roman has to do with these extreme TNOs. I mentioned them earlier. They are objects on very large orbits, such as Sedna. And they, most of them have been discovered near their perihelia when they're closest to the sun, obviously when they're brightest. And they have, those perihelia are large enough, they're beyond 40 AU, that there is no dynamical way that we can explain that they could have been placed on those current orbits through interaction with Neptune, as they are no longer currently interacting with Neptune. So this idea put forward by Badigan and Brown back in 2016 was that the observed extreme TNOs all seem to have their perihelia aligned, and that was pointing to the potential for a large unseen planet orbiting at hundreds or thousands of AU. So this is the picture, and I've twisted it on the side for a reason I'll show you in a second. This is the picture back in 2016 of the number of known extreme TNOs was relatively small. And here's the picture now So I tried to line them up. We know about a few more of them now. It's still a small number. We're talking maybe 20 or so maybe 24 of these objects. We see now some objects orbiting at orbits that are anti-aligned to the ones used in the paper to describe this unseen giant planet. Doesn't necessarily this doesn't necessarily mean that that theory is incorrect. This is still a possibility. The anti-aligned objects can still exist if there is a giant planet, but there's still obviously an observational bias in the objects that we can detect because they have to be closer at perihelion so that we can actually see them. So how can we expand the number of objects, hopefully observe some of them further from perihelion? Because if we're seeing this many objects at their closest point, there must be an extremely large population orbiting closer to their aphelia. Can we necessarily detect those? Not really, but maybe a little further from perihelion. Help reduce some of these observational biases. So I submitted in fall last year an idea for the Roman early definition astrophysics survey. This idea that I call Rosette, the Roman survey for extreme TNOs. The idea is to observe more of these objects at further distances to reduce the observational biases. And a secondary goal is to try to use Roman to detect objects that are beyond the Kuiper cliff. This Kuiper cliff is beyond the 2-to-1 resonance with Neptune, so about 50 AU from the sun, where we see a steep drop off in the number of objects. There's a possibility that there could be more objects out there, and it would certainly say something about the formation and evolution of the solar system in its early days. So the idea would be to stack four WFI fields, perhaps in the way that's shown here on the right, which are cover about 1 square degree, and take 10 1,000-second exposures with the widest filter. And this would result in observations at 95% efficiency. So only 5% overheads. For comparison, if you want to do the same sky coverage, so 1 square degree, it would take 100 NIRCam mosaic tiles on James Webb. And that's using both the A and B modules, as well as multiple days of exposure time. And that would just be to get to a 50% efficiency observation. So 50% time dedicated to overheads. Since these objects are moving so slowly, you'd have to return over, perhaps days to look for movement of these objects. So come back over 3 different times. And in about a month of observing time, you could cover 20 squared degrees and observe potentially up, over 100 new ETNOs, increasing the number by an order of magnitude. And this would be to a depth of Sloan R 28.5, which blows out, blows the OSOS and LSST detection limits out of the water. Smaller sky coverage, obviously, but deeper within that sky coverage. And I buried the lead perhaps a little bit here, but I just wanted to put in a plug for why solar system observations are important components of astrophysics, astrophysical telescopes programs. So here's, for HST cycles 22, 24, as well as the press breakdown in the same time period. We have 7 times the number of press releases related to solar system observations compared to the number of orbits that are given for them. So this shows that the success of a mission, you can make it more visible to the public through solar system observations. And a solar system solar system observations with astrophysics resources are crucial to that success. And one last slide here, just showing synergies with other observatories. Obviously, Roman provides full sky coverage, whereas the Rubin Observatory provides sky coverage in the southern hemisphere. So there's a complementary there, especially in the overlapping region along the ecliptic. And then with James Webb, you can follow up on new discoveries with Roman to look at spectroscopy, things like that, to get surface compositions, etc. And here's my last slide. As I promised, here's a QR code with, all you have to do is hold up your phone camera, and it'll take you to the archive article, and hopefully a sequel coming at some point in the next few years to that one. So thank you for listening, and I'm happy to take any questions now.
Great timing. Thank you so much for your talk. We have 2 questions in the chat. As a reminder, you can post more questions in the chat or on session 7 on our Slack. I'm going to take the questions in reverse order because I haven't follow up on the question number 2, or perhaps a premise, and that's about TNO occultations. Mm-hmm. So the question is, by Rangar and Cherry, I believe 5 Hertz is too slow for TNO occultation. In the past work needed 30 to 40 Hertz. Do you think the subarray mode for Roman is really competitive? And my additional question about occultations is that I think there was a paper by Alessandro Morbidelli, recently in 2020. I've been not working in this field for some time, so I'm not so sure, but if I remember correctly, it predicts a very slow slope of the size distribution down to something really small, like 10 meters, which will make the event rate really, really low. So do you have updated event rate that follow this model?
I don't have any of that information. That particular slide on the serendipitous occultations was taken from the 2018 paper, which was essentially a review paper, and someone else provided that information. But yeah, the 5.8 Hertz obviously is not terribly fast. Let's see, let me go back to, so yeah, it'd be harder to observe very small targets, and I guess it's faster than was available for the FOS guiders on HST, and there were potentially 1 or 2 different events that were detected even at those slower rates. So there's a little bit of massaging you have to do with those data, I believe, to try and confirm a detection. But if you can get a single point, that's more than we have currently. Obviously not a fully designed experiment, right? But it provides the possibility to detect more of these small objects. It's a little outside of my usual realm of study, but.
So maybe if I can add to that, at opposition, the duration of the event is about 0.2 seconds in a fully diffractive regime. So you're right, 5 Hertz will give you 1 point. Yep. Away from opposition, the speed of the object slows down, so you get a longer event in time and a correspondingly lower event rate, of course.
Yeah, so hopefully somewhere between 1 and 2 points, right, along the shadow. Yeah.
And the other question, if you can answer it quickly, it's 11:30 on the dot. The Earth Trojans can occupy a surprisingly large region of observational phase space. Have you made any estimate of how much time an X% complete survey would take on Roman? If you can give a 2 seconds answer and then maybe expand on Slack, that would be great.
Yeah, as I said, I hope to have a sequel to the previous paper where we delve a little deeper into some of the numbers. So keep your eyes posted on that. I don't really have a number, amount of time or anything like that, but it's something I certainly want to look into. So.
Thank you very much. This brings us, let's give a round of applause or some hand signs with your emoji and reactions, please, to Bryan for his great talk.